If you've ever tried to understand general relativity and walked away more confused than when you started, it's probably because most explanations skip the one idea that makes everything else click. Before Einstein got to curved spacetime or black holes or any of the big stuff, he started with something almost embarrassingly simple. A person falling can't feel their own weight. That's it. That's the seed. Once you sit with that observation and follow where it leads, general relativity stops feeling like abstract math you could never grasp, and starts feeling like the only logical conclusion. And it all begins with a question about falling. So here's a question that sounds almost too simple. If you emptied your pockets and dropped everything at the exact moment you started falling, would any of it fall faster than you? Your instinct might say heavier things fall faster, and for a long time, people thought Newton would back that up. He wouldn't, actually, and that tension between what people assumed he said and what the math actually predicted is where Einstein's whole rewrite of gravity begins. Newton's version of gravity ran the show for about 200 years, and honestly, it earned that. It predicted planetary orbits, explained the tides, traced the arc of a cannonball through the air. The equations worked so consistently that nobody felt much pressure to ask deeper questions about what gravity actually was. It was a force, invisible but real, pulling things together across space. That was enough. But Einstein sat with something most people had glossed over. Experiments going back centuries, with lead weights and pendulums and objects of completely different compositions, kept showing the same thing. Everything falls at the same rate. Physicists call this the universality of free fall, and it applies to any uncharged test body, regardless of what it's made of. So if you're sealed inside a box and that box falls freely, every single object inside drops together. Your phone, your keys, a bowling ball, a feather with no air resistance. From inside the box, nothing feels like it's falling at all. You'd float, and there'd be no way to tell, from inside that box with no windows, that gravity was doing anything to you. Because everything around you is doing the exact same thing you are. That's not a weird edge case. It's telling you something real. If gravity completely disappears the moment you fall freely into it, then what you normally call feeling gravity isn't gravity at all. It's the floor pushing up on your feet. The ground stopping you from falling is the force you feel. And gravity itself is just the natural path things follow when nothing gets in the way. This idea has a name: the Equivalence Principle. Einstein described it as the complete physical equivalence of a gravitational field and an accelerated reference system. A rocket pushing you upward at just the right rate produces every sensation you'd feel standing on Earth. The pressure in your feet, the weight in your limbs, the way objects drop when you let them go. And no experiment you could run inside either one would tell you which situation you're actually in. So, if a gravitational field and an accelerated reference system are completely equivalent from the inside, and acceleration is just how motion changes through space and time, then gravity must be doing something to space and time themselves. To understand what that actually means, picture a marble rolling across a flat table. It goes straight because the surface gives it no reason to turn. Now put a heavy bowling ball in the middle of that table, but make the table out of something soft that bends under the weight. Roll that marble again, and it curves toward the bowling ball, not because the bowling ball reached out and grabbed it, but because the surface itself isn't flat anymore. That's the core picture of general relativity. Mass bends the space and time around it, and everything else just follows the straightest path available on that bent surface. What looks like a curve from the outside is actually the most direct route through a geometry that's no longer flat. And it's not just bending either. Near a spinning mass, space-time also twists, a bit like wringing out a wet towel, dragging space around with it as it rotates. Most people get stuck here because the rubber sheet image only shows space bending. The full picture bends time too, and the time part does more work for everyday gravity than the space part does. Near a massive object, time runs slower, and physicists call this gravitational time dilation. It's not a feeling or a perception. It's physically measurable. A clock on the floor of a building ticks slightly slower than a clock on the roof because the floor sits deeper in that curvature. So when you ask what it means for gravity to be the shape of spacetime, think of it this way. In flat spacetime, the most natural path through time is also straight through space, so you just sit still. In curved spacetime, near a massive object, that most natural path tilts toward the object because time runs slower closer in, and your path bends toward where time is slowest. You're not getting pulled toward Earth. You're following the most natural route through a geometry that points downward. This is exactly why light bends around massive objects, even though it has no mass. Light always travels the straightest possible path through spacetime. So if spacetime curves, light follows that curve through a geometry that's been reshaped by mass. Einstein captured this in his field equations. Mass and energy determine the curvature of spacetime, and that curvature determines the trajectories of everything moving through it. Planets don't orbit the sun because something yanks them in a circle. They coast along straight lines through a curved geometry, and those straight lines loop around the sun because the sun carved that shape into the space around itself. And if that's true, it means you could actually test it. You just need to watch light bend around something massive enough to measure. The most direct way to test that was to watch starlight bend around the sun, and scientists found a way to do exactly that. You can't photograph stars near the sun because the sun is too bright. But during a total solar eclipse, when the moon slides in front of the sun completely, the sky goes dark enough that stars near the sun's edge become visible for just a few minutes. So scientists would photograph those stars during totality, then compare their positions to photos of the same stars taken at night, when the sun wasn't anywhere nearby. If the position shifted, light was bending. The first time this test ran, the results matched Einstein's prediction closely enough that newspapers around the world ran the story. But the early measurements weren't clean. The equipment had real limits. The margin of error was wide, and plenty of physicists weren't fully convinced. The question of exactly how much light bends around the sun stayed open. Modern radio telescopes and space-based instruments eventually pushed the precision much further, confirming the bending to a tiny fraction of a percent. But scientists kept going back to the eclipse method anyway, because there's something direct about it. You're doing almost exactly what the original test did, just with better cameras. In April 2024, a team spread 13 telescope stations across Mexico and Texas during a total solar eclipse, using modern digital cameras capable of taking thousands of images in just a few minutes of darkness. One station in Mexico captured images of 171 stars during the 4.5 minutes of totality. The team measured a deflection of 1.84 arcseconds, compared to Einstein's predicted value of 1.75 arcseconds. High-altitude clouds and wind disrupted several stations, and one was completely blown over, but the measurement held up. What made this effort worth paying attention to wasn't just that it worked. The team used open-source software, calibrated their cameras carefully across multiple nights, and worked out in detail how lens distortion alone could produce a fake signal if you weren't watching for it. The 2027 and 2028 eclipses are already being planned for, because the sun's path during those events crosses sky regions packed with bright stars, giving future teams a real shot at imaging stars inside the forbidden zone, within one solar radius of the sun's edge, where the bending is strongest and the hardest to measure. And if you can measure gravity bending light from space, it turns out you can also feel gravity's effects from your own pocket. Your phone is one of the clearest places to see general relativity working in the real world. GPS satellites orbit Earth at high altitude and move fast, and both of those things mess with time in ways you can actually measure. Moving fast makes their clocks run slightly slow compared to clocks on the ground, because of special relativity. But sitting farther from Earth's mass makes those same clocks run slightly fast, because of general relativity. And that second effect is bigger than the first. If engineers had ignored it, your GPS position would drift further off with every passing day. So every time your phone locks onto your location, it's running corrections that trace directly back to the same equations Einstein worked out while thinking about falling elevators. The engineers who built GPS didn't include those corrections as a formality. Without them, the system fails. Time running slower near a massive object isn't just a GPS problem, though. It scales. The deeper you sit in a gravitational field, the more curved spacetime is around you, and the slower your clock ticks compared to someone sitting farther out. Near a black hole, this gets extreme enough that someone watching from a safe distance would see a person falling in, appear to slow down, stretch out, and freeze right at the edge, a boundary where nothing, not even light, can escape. The person actually falling through wouldn't notice anything odd at that boundary, assuming the black hole is large enough. But the tidal forces near a smaller black hole would stretch a person lengthwise and compress them sideways, a process physicists call spaghettification. Both experiences are real. Space-time curvature just makes time run at genuinely different rates, depending on where you are. An astronaut in orbit and a skydiver in freefall feel exactly the same thing for the same reason. Neither one has a floor pushing up on them, so both are weightless. And the astronaut stays up, not by being held in place, but by falling toward Earth continuously while moving sideways fast enough to keep missing it. General relativity has held up against every test physicists have thrown at it for over a century, from gravitational waves to black hole images to pulsar timing. But at the center of a black hole, or at the very start of the universe, the equations stop giving useful answers. And that's where the story of gravity gets genuinely unsettled. None of this started with equations. It started with a simple question about what a person falling in a sealed box could actually know. And following that question honestly led to the conclusion that gravity isn't a force at all, just the shape of the space around you. Scientists are still checking that conclusion right now, with eclipse cameras, atomic clocks on satellites, and detectors picking up ripples from black holes colliding a billion light years away. The floor pushing up on your feet is the force. The falling is the freedom. And that curve in the fabric of the universe is what we spent 200 years calling gravity.